So without further ado, it's my pleasure to introduce our first presenters, Stan Schneider, CEO at Real-Time Innovations, and Thomas Krueger, team lead and lead developer, Human-Robot Interaction Lab at the European Space Agency. Stan, Thomas, I turn it over to you.
Yeah, thanks for the nice introduction. When we talk about space robotics, sometimes imaginations run wild. Of course, we have all the science fiction elements, but of course, we also try to dream realistically, where we think we want robots to go where it's too dangerous for humans and want to do tasks that we currently can't. But there's, of course, the reality aspect of it. If we have a few examples, this is the first remote-operated robot from the Russians. It was in the end of the 60s and the 70s on the moon. We have, indeed, in this picture, two robotic vehicles, if you want. One is the arm that is on the space station, and the other one is, in a certain sense, a fully automated spacecraft that reaches the space station. Of course, probably known to everyone, we have NASA, to be fair here. NASA flew 5 robots to Mars, and the latest addition is also a mini helicopter on Mars. And of course, robots on Earth, we also have them, and in the end, we have usually the 4Ds. We want to do work that is too dangerous, too far away, too dull, or too dirty for humans. Good examples are factory automation, which is also here a bit of a special case because it's in a structured environment, or we have bombs that help for bomb defusal. We see here underwater robots, also well established. Here, repairing the blowout preventer or try to repair the blowout preventer at Deepwater Horizon accident. And of course, we have space. And even if this picture is quite beautiful, it's also a reminder that the environment out there is quite harsh. I mean, we have temperature fluctuations, we have hard vacuum, we have radiation. So we want to send the robots where it's too dangerous. Another design factor is, where do you have the robots? Okay, we have the Earth, and if we go one step further, that would be low Earth orbit, our space station. We can imagine robots on the moon and on Mars. But one really factor that influences how we operate these robots is the latency. And if we operate in low Earth orbit, in theory, it would be a millisecond, but in practice, with a direct link, it would be 20 to 40 milliseconds of round trip. If we go via relay satellites, it will be indeed 850 milliseconds for the signal to go back and forth from a certain point on Earth. In the moon, of course, the same here, speed of light would be 2.6 seconds, but we need infrastructure, relays, and so on, which a healthy estimate would be 3 to 5 seconds. And if we go to Mars, there it becomes even more difficult. So in the ideal case, we have 8 minutes that Mars and Earth are lining up. But of course, if they're on the opposite sides of the sun, we have 40 minutes. And this kind of defines a bit how we can operate the robots. Of course, on Earth, low Earth orbit, and Moon, we have teleoperation. For all scenarios, we have supervised autonomy. This is a mixed form where we, let's say, give little tasks to the robot to perform certain things. So, for example, going from A to B would be an example for supervised autonomy in case the robot can actually handle navigation on its own. And of course, autonomous systems, fully autonomous systems work on every time delay. But indeed, the further you go away, the more they are required. And so I'm in a small R&D lab inside ESA, and we had a different approach to this whole robotics and autonomous vehicles. And I would like to take you on the journey, how we approached it, and maybe find a little bit of a different perspective. And also, to be open and honest here, ESA had a few setbacks, so I'm in a small R&D team, but the big space-grade system is still needs to be launched. When we looked at it and we had a dream that we want to build infrastructure, we had a good look in 2010, what can robots really do? And I hate to say, but I'm a roboticist by heart, but we have no meaningful agents that could go to the moon, build infrastructure, do this, and this is simply not possible. The astronauts, of course, want to do everything themselves, but of course there we have the problem. We need to fly them to Mars, we need to land them, they need to survive, we need to bring them back. So the only solution that actually came up is we have this vision. We send orbited spacecraft with robots and humans on board. We send the robots down, remote operate them from orbit, build infrastructure as we want, leave the robots on the surface, and the human can go. So this is the scenario that we started researching it. And teleoperation, as said, we have some well-known examples on Earth. It can be the robot and the control station in the next room, around the corner, on a boat, underwater. There are various scenarios. And if we now look back to this, we basically didn't look what anyone else did. Of course, autonomous systems, the holy grail of robotics. We indeed really focused what can we do with teleoperation following this scenario, and of course expanding then to more mixed mode like supervised autonomy, where it's a mix of all of these elements and we can go stepwise as far as we can. And of course, we have our scenario, the dream, robots or geology on the moon. And for us, as a small R&D lab, we thought, how can we approach this to come up with a good guess? On the moon, there would be the Lunar Gateway, hopefully will be launched at the end of the 2020s. So the astronauts on the Lunar Gateway would control the robot on the moon, of course, with ground support. And the ground can, of course, with a higher delay, maybe access some teleoperation functions. And then, of course, as a research lab, we approached it. We say, okay, we built a demonstrator. And as said here, this is a demonstrator. This robot will not go to space, but it would be a good guess of features and especially software interfaces, what we could do. We don't also have the Lunar Gateway yet, but indeed we have the International Space Station. So our test was designed to have a robot control from the space station, have an astronaut on the space station who control our robot on ground. And of course, with scientists in the loop that, like in a real scenario, advise the astronaut on what to do. And of course, having it somewhere in controlled environment is often not enough. So we went a step further and we went with our robot to Mount Etna. And the idea is there that there's really a scenario that people hide rocks, set the astronaut and the rover there and let them really find the rocks or the geological samples that they have hidden. So this, of course, will be a bit blown up. So there's an operations center, that is scientists that supervise all of these things. There's only one thing. Logistic is a nightmare to get astronaut time and have the robot on Mount Etna. So we took one step back and the astronaut was operating here from a hotel room. But it is quite representative. And so with this scenario, it of course becomes more and more complex. But in the end, if we talk about teleoperation, we have, of course, from my perspective, the controller and the robot. But of course, there's something in the middle. I have many words to describe it, but it's a very important element. And from robotics perspective, it's often we're excited about robots and safety and the science that we get out of it. But we overlook this link. And to build really systems that are scalable and maintainable, we really need to focus on the link. So I kind of did all of these mistakes in this area, but we learned a bit how to make it more maintainable, secure, and scalable. And at this part, I would like to hand over to Stan that, would explain more about the middleware.
Hi, so I'm Stan Schneider from a company called Real-Time Innovations. I'll talk about a little bit, but I want to talk about sort of how we bring this down to earth. Actually, maybe I'll really bring it down to earth. Down to earth. So the problem on Earth, you can be more autonomous. So this is sort of cool. And but the problem is there's situations where you can't really always handle everything. There is no such thing as truly autonomous. Just like there's no such thing as truly happy. Autonomy is sort of like happiness. It depends on your environment. You can be happy at home but not at work. Depends on what you're trying to get done. You can do some tasks, other tasks, but there's no such thing as truly autonomous. There's always something you're going to run into, and that is known as a world of corner cases. This is the best image I could get for a world full of corner cases. Corner cases are things that you can't really plan for in advance and become very hard to deal with, and they're everywhere. The systems are very complex. Things change. You have to know what's going on. It's really hard to do this, and because of that, people get really frustrated, really difficult to make it work in all these different cases. But we still want to be able to get some levels of autonomy and some levels of intelligence out there in the real world sooner, and fundamentally one way to do that is to get them remote help. And we've learned a lot from teleoperating robotics. Space robotics have been teleoperated, at least in research, for decades now, and a lot of that technology can be used in many different places. So if you actually look at what's hard about it, first of all, you've got communicating with moving vehicles. There's a lot of software involved. Handing off the communications between the two modes tends to be really important. There's different kinds of data flow, and then the networks sort of change, and you transition networks and things like that on Earth. Every time you move cell stations or something, you get a different IP address and have to renegotiate, and those kind of things become very debilitating. So really, that's the fundamental problem. We're trying out. RTI works on that. So my company's called RTI, Real Time Innovations. We have infrastructure software. We're actually the largest infrastructure software for what I call the smart world. IoT little devices aren't really what we're talking about here. We're talking about building systems with many devices and many communications that have to share information. We're really trying to enable connecting AI and smart algorithms, what I call functional AI, I can define for you, like with distributed devices in a single system. Give you an idea what we do. We started out in the autonomous vehicle world, a spin-off of the Stanford Aerospace Robotics Lab, doing space robotics, amongst other things. And now we do lots of different kind of vehicle designs, flying things, about 100 of them are flying things, but also underwater vehicles, surface vehicles, mining vehicles, construction vehicles, delivery robots, on and on and on. It's an amazing variety of things that you can do with a little bit of autonomy that can get better. More recently, we were working on road vehicles that carry people. Most of our customers there actually aren't trying to do high levels of autonomy. They're trying to do software-defined vehicles. Anybody know what a software-defined vehicle is in the room? See if we're automotive people here. Not a lot of them. We also do medical systems, medical robotics, hot market. Also very expensive, big problem projects, imaging device, patient monitoring systems, lots of defense systems, 400 different kinds of defense systems out there. We run Canada's air traffic control. If you've flown to the U.S. from here, you've been through that. And NASA's launch control, we do lots of things for NASA. That's one of them. And also a lot of power and renewable energy stuff. So you get an idea, we're 2,000 projects we have experience with, about 300 employees, which for this industry is pretty big. So does this picture look right to you? Anybody look a little bit funny? Anybody know what's wrong with it? Usually a group this size, someone will figure it out. It's upside down. It's a reflection in the lake. And I put this here because it's really our way of looking at the world. Most systems are designed around the system. People talk, well, I need a server. I'll put a server here. I need networks. I need firewalls. They talk about system components and then figure out what data they're going to send over that component. We find that really hard. In fact, once you've seen it this way, if I put it back the other way, it's really obviously wrong now, right? So you'll never be able to see it again. Once you sort of get the idea what data centricity is, which is what I'm talking about here, you design the system around the data rather than the other way around. You're actually used to it because databases are data-centric storage. So you're very used to data-centric technology. You just think of it as storage. We're trying to think of it as a way to communicate, not just a way to store information. So think of it as, data in motion rather than data at rest, but it's still the same kind of idea. Anybody in the room technical, any engineers? So for those of you who aren't raising your hands, anybody have a hand? Let's see how many people have a hand. Raise a hand if you have it. Oh, most people are here. Okay, at least you're paying attention. That's good. If you're not an engineer, this is my most technical diagram. Not quite, but it's just two boxes. And the whole idea of data centricity that virtually makes it look like if you're writing an application, an algorithm, or a sensor or whatever, it looks like all the data you need for your distributed system lives in your application, in your memory, and your language, and your chip architecture for your operating system. You can just read and write it. It's through an API. There is a little bit of a trick. You have to tell us what it is first, but we're going to take that information. Now we know where everything has to go. We have the right data at the right place at the right time. Fundamentally, we're trying to do so it looks to you like it's a virtually in-memory data sharing. So most systems look like this. They have some algorithms. Some of them are more intelligent than others. You want to be able to write those as if all the data is available to you. They almost all have some way to see what's going on in the world, sensors, some way to change what's going on in the world, actuators or motors. And most systems, when they get complicated, need to have operator interfaces. Sometimes lots of them, like you saw with that Canadian air traffic control, hundreds of screens that have to get the right data at the right place, the right screen. Fundamentally, what we do is we know that the sensor is producing information. We take it, we stick it in the memory of the algorithm. Actually triggers the algorithm, but it gets there right on time, and then it takes that, puts it in the memory of the actuator software here just before its loop runs. So it looks to all of these things as if that data was already there, and they can just execute that. With this little thing, you can control a loop, close one loop. Of course, we're doing that with all the data in the system. Lots of data flowing around. We have systems, we call these things flows. We have systems with 10 million flows. It gets very complicated out there. And the whole trick is to still make it look like you can write each of the pieces independently as data-centric. There is a standard out there called DDS. There's 18 implementations that I know of. There's probably more than that out there somewhere. At least 5 or 6 of them are commercial, well-supported versions, and lots of other not-so-good ones. It's run by the OMG, which is the largest system software standards organization, and actually founded this show. I was actually part of that way back when there's something called the IoT, Industrial IoT Consortium. We created this IoT Solutions World Congress quite a while ago. I'm not going to go through all the advantages of data centricity, but I'll talk about a couple. And one of the things is, if you think about it, that the data looks like it's in your own memory, one of the things you can do pretty easily is, well, it can move. And you can actually change networks, and you don't have to renegotiate security parameters when you do that. You don't have to renegotiate, you'll lose your memory, persistence and things like that. You can move around. More specifically for this application, if you talk about teleoperations, so you have a sensor here. We sometimes draw it as a data bus like that. And the sensor is producing information and sticking it in the memory. We're putting in the memory of all the different components, so the algorithms and the teleoperator here and in the actuators. And then you have this concept of strength. It's actually called strength of ownership. So this algorithm is going to publish what it wants the system to do with strength 10. And of course, the actuator has to know that, so it's going to send it to the actuator so it can do something. But along comes teleoperation. It can have a higher level strength. So you turn that on, and it can seamlessly take over the system and override that and now run with the other thing. It's not quite that simple because you have to make sure the states are all consistent across all these different nodes. But with this very simple called quality of service of strength, we can now take over and do handoffs between modes of the system that might require different inputs in this case. The DDS standard, actually the very first application was for sensor data fusion, taking 20 different radars and figuring out there's only one thing you're looking at there, and radars and video and LiDARs and things like that. You can tell what's going on. If that shuts down or fails, it automatically picks up the other one again, so the system can be redundant or make it easier to run things. So there's 21 of these things, 20 plus if you different versions of the standard that do many more things than just strength. It can do a lot of timing things, like how often signals are going to be updated, detect when sensors are not live. Very different to have a sensor that's not live, not giving you information, than a sensor that doesn't see anything. If you think about it, you don't want to hit a pedestrian just because your LiDAR goes down or something. It does that. Reliable, liveliness, ordering, even security are all these things. Another good example, these systems get complicated and the data flow can get very complicated. This is sort of typical kinds of sensors you see in an autonomous vehicle, in a vehicle, and they have different rates and they have different latencies and they have different volumes of information. And if you sort of start with the system thing, where I'm going to start with my network and my servers and all these kind of things, you end up with multiple networks and having to have gateways between all of them. But you can, if you think of it as a data-centric problem, and you can set quality of services to do things like know what rates things are at and how much throughput you're going to need from it, you can handle it all with a single data bus that makes that work. It simplifies, it greatly simplifies how these kinds of systems work, which is why the software-defined vehicle automotive world is very much picking this up. You can also let applications specify their requirements. So you might have an enterprise network that has very high performance here, and your applications can use that. And if they don't use that, you don't need it, and it can work elsewhere. But you can also have a satellite link that only works very low bandwidth, high delay, lossy, called DIL. If anybody's heard that acronym, disadvantaged, intermittent, and lossy, that you can still do communications. This is actually pictures from NASA's very similar experiment to what they run for the space station astronaut controlling an ESA robot. So it's out there. The important thing is, as long as the quality of service needs are satisfied, you don't have to inform all the parts of the system that the communication channel has changed. Obviously, these are quite different, but in many different cases, you can switch communications channels, switch networks, switch cellular networks, and it's completely seamless to the devices underneath it. It's one of the magics of DDS. And with that, I'll let Thomas tell you why it's important to him.
Thank you. Yeah. So with this introduction of the global data space, so this was also the architecture that we followed in the end with our rover. Of course, we use commercial components. So the first thing that we usually do is we write a kind of what we call a proxy that more or less translates between the industrial hardware, and we put it to the DDS data space. So here we have it, for example, for the cameras, for the robotic arms, for the GPS. This is on the robot side. And of course, on the astronaut side, it's similar. There it's a bit smaller. We have a Qt application displaying the video stream and interacting with the user, and the Simulink model, because for all this control and filters, it's generated code, but of course also has a DDS interface. And now is then the question, how can we combine these two elements? And here the middleware really plays a crucial role, because now we can be really agnostic if it's in the lab Wi-Fi where everything is good, if it's with 4G or 5G, or if it indeed goes over this KU forward link to the ISS with 850 milliseconds round trip and quite bandwidth restricted. Okay, spoiler, yeah, we could do this. This was quite a success. And to emphasize a bit, it always goes from simple to complicated. If you want, we said, okay, we need the data going from experiment location to the space station. But indeed, then there comes a user center that wants the same test setup to operate from there, our robot. Then there are different requirements because the traffic to the space station is heavily netted. Can we tunnel through it? Then security requirements, you need to encrypt the data. We have operations center that also want to listen in, but sure don't to mess up. And like we said with the scenarios, we have time delays and different scientists that see different data at different time spots. So these experiments get actually quite complex, quite quick. And also, we are a bit in a conservative environment where we are not yet used to this modern technologies of publish, subscribe. So it also is a bit on the political side to convince, can we run this inside your data structures? In the end, what we did with DDS, of course, fast, the telecommands for the haptic and force feedback is really important. Video is crucial, of course, for an operator like this. And of course, we want to record all the data and kind of pick the all-in-one solution. And besides the pure transmission, the tooling on the side, I mean, I can tell is also really important for all the developers to move forward. So we based most of the system architecture on DDS. I mean, to be fair, almost for some difficult network aspects. At that point, we need to use OpenVPN, but I think now in the meantime, there are solutions available, and file transfers and other things we reverted to standard protocols. And here to give you a little bit of an impression how it looks like. So this is the astronaut. We see this white device is the robot control. This is, yeah, what the astronaut basically sees, assembles a rock. Here in a controlled environment in the lab. So there's rock picking and driving, and to fulfill the task that was given. And of course, then we moved from that environment to Mount Etna, upgraded the rover a bit with bigger tires. And it's really not a black and white image. It really is like this. It really feels like that you're on the moon, and also exemplary the rock picking at the same location. And of course, all went well. And here's a bit more impressions how it looks like. So then indeed, multiple locations, multiple control rooms, all seeing the data. Yeah. And at the form that they basically the end consumer wants. And the question is, with this architecture, how now could we move quicker to automated vehicles. So we had all of this in place, and let's say now we want to move to more autonomy. So we have a state estimator that gets fed from the IMU data and the GPS data. On top of the state estimator, we can uses the LiDAR data to compute the map. And from a map, we could have an agent that does the auto navigation using the map, and now just interfaces with the locomotion system like the joystick operator before. So this is now our step, how we enhance our system. And of course, this never ends. Now our next experiment, we have actually heterogeneous robots. So we need to think about a data model that works not only on one robot, on multiple robots, how we scale it up, how we deal with bandwidth. And we are pretty convinced the middleware plays an important role in this. Just a side slide, also times are really changing. Now we have unprecedented communication all around the globe. There are more and more robotic systems. So a lot of these things are actually in the flow. And for the sum up, I would like to hand over to Stan.
So if you think about the diagrams he was showing you, these systems get complex really fast. I showed you a very simple little loop with only 3 points, but they can get many, many different points and have different modules, and they have to evolve over time. And all of those things, if I go back here real quick to this diagram, this kind of thing is really easy if you think about just data flows. You don't have to worry about servers or networks and all that kind of thing. You can define, we call it a data model, which looks like a database table, actually. It has a definition of the data, along with all the quality of service. So timing, how fast this data. You can't tell a database this sensor information is going to be updated 100 times a second. You can tell that to us, to the DDS. It must be updated 100 times a second, or maybe 1,000 times a second. I can't handle that. It'll actually downsample if I want it only 100 times a second. I mean, very intelligent about managing all these flows. So diagrams like this become quite easy for the end user, the end programmers, to build it. So I'll slip through that. So fundamentally, if you look at autonomy, like I said, autonomy isn't the level 1, 2, 3, 4, 5. I'm not a big fan of the levels because nobody can really define what that is. And that's because autonomy isn't a well-defined thing. It sort of depends a lot on the environment, depends on what the task is, depends on how complex it is, what the corner cases are. They get very complex quickly, but they all are going to need, at least for the next 50 to 500 years, some kind of remote help capability. And if you have a network and data infrastructure underneath it that makes that easy, so you can do things like support handoff and handle challenging data flows that are different kinds of rates and performance, and work over connections that you can't always rely on, you can make these systems much more buildable. And if you remember nothing else here, remember data-centric architecture. Data-centric architecture. You can also remember RTI, that's good. And ESA, you already knew ESA, you didn't know RTI, but RTI, data-centric architecture. And I'll be proud of you. That'd be great. So connect with me on LinkedIn. It's the easiest way. But Tomas is also on LinkedIn. He got a better handle than I did. And I think we have a few minutes here for questions if you have questions out there. Mic there. Thanks, Ledu.
Hello, great presentation. This is Wasim Gadban, Global Vice President for Innovation and Digital Engineering at Kent. So we are working on autonomous operation as well in the energy sector, mainly in oil and gas, where we want to transform especially offshore fields to unmanned fields. And the challenges, so we designed the AI autopilot, that's totally fine, but challenges is about the emergency response, where I see that teleoperation is a solution for that. You know, that you need some maintenance team to intervene to fix like the task required. So did you work in the energy sector in similar kind of solutions? What's your recommendation here?
Yeah, we've done quite a bit in the energy sector. I mean, you showed that underwater robot's actually running our software that's doing repairs of underwater oil systems. We also work with mostly upstream drilling, intelligent drilling systems, things like that. Not a lot midstream and downstream. Happy to talk with you afterwards. It's not it's a very slow sector for us. So we worked a lot with Exxon a while back, and if you look at RTI Exxon, you'll see all sorts of papers we publish and stuff, but it just, the refinery end of it is just very slow. No great technology drivers there. Maybe you've got a better example. That'd be great.
Any other questions? Well, if not, let's thank our speakers, Stan and Thomas.
Thank you.